When it comes to space travel, the ultimate fuel isn't something we mine or refine. It's something that annihilates everything it touches. But if we can harness it and use it safely, antimatter could be the key to reaching the stars. So why does antimatter keep showing up whenever we talk about near light speed starships? The appeal is simple. Most rockets are about throwing mass away fast. Antimatter is about turning mass into the ultimate rocket exhaust, particles moving at or near the speed limit of the universe. That's why it shows up in every near light speed starship discussion, right along things like laser sails and Kugelblitz black holes. It's one of the few options where math even allows you to play in that league. And you've heard the usual version. Matter touches antimatter, they vanish in a flash of gamma rays, and you ride that light like a torch drive. The trouble is, that's the clean and simple version that I think leaves out a lot. For starters, real annihilation doesn't give you one neat exhaust plume of convenient photons to reflect out the back. It gives you a whole grab bag. Pions, muons, neutrinos, gamma rays. Basically whatever the particle zoo can cough up given the energy and the circumstances. Some of those products are great for propulsion because they can be reflected, or they're charged and you can push them out the back with magnets. Others, like neutrinos, are the opposite. With known physics, they're almost useless as a propellant, because they fly through everything and refuse to be steered. But that same ghost through matter trick is also what would make them amazing. If you ever had clock tech that could reflect or collimate them, you could have a near light speed exhaust you can't melt your engine on, and you could stand behind the rocket plume unscathed. We don't have that, so for now, photons are the best game in town, and preferably the lower energy ones. We'll discuss that later, but we should start by clarifying why high-energy photons are an awesome propellant. And that's because post-annihilation, they emerge containing the full mass energy of the annihilated particle and moving at light speed, which in rocket terminologies means a light speed exhaust velocity roughly 100,000 times faster than propellant particles coming out of your typical rocket nozzle. To put that in momentum terms, when it comes to momentum transfer, if we imagine a bare proton, it carries about 5 times 10 to the -24th kilogram meters per second of momentum. And the ship it left has gained the same backwards, and yet if that was converted into a photon, it would have 1.5 times 10 to the -10 joules. And photons are nothing but momentum, in spite of having no mass, and its momentum would be 5 times 10 to the -19 kilogram meters per second. 100,000 times more momentum than that proton gave. I should also note that photons are an awful propellant for low-speed rockets. On this show, we often contemplate using laser sails to move ships to very high speeds. But you wouldn't for low speeds, you instead use that same energy to simply superheat some propellant to high speeds. That proton propellant of a moment ago, moving 3,000 meters per second, had a kinetic energy of 7.5 times 10 to the -21 joules. So if a photon of that proton's mass energy, 1.5 times 10 to the -10 joules, gets absorbed by 20 billion protons, they would all have the same kinetic energy and momentum of that proton moving 3,000 meters per second, which is obviously way better as a use of energy. It's as we get to higher speeds, and while having to carry our fuel and propellant, that the rocket equation makes that untenable. But it's worth noting that, unless we get a truly awesome way to make and store antimatter, it is likely to be vastly more expensive than alternatives, and thus we are likely to see it being used sparingly and in conjunction with other processes. An example of that will be antimatter catalyzed fusion, which we'll get to later. It also might be a multi-stage type of propulsion, ones that don't necessarily have to follow the rocket equation, like beaming photons or other particles at a ship while it's still close enough the system is departing from to be targeted by an emitter. The main point of antimatter in discussion of its use as a starship fuel, or as a weapon, comes down to its energy density. In that regard, the rocket equation makes antimatter a better fuel than a weapon, because nuclear bombs are already extremely energy dense, and you can't simply build a bigger one. If antimatter costs 100 times more than an equal energy release from a fusion bomb, it makes more sense to build a larger conventional nuclear weapon instead. If you need a micro-nuke you can hide inside a ballpoint pen though, antimatter is your way to go because it is so energy dense. For comparison, chemical rockets like the space shuttle's main engines generate energy through hydrogen and oxygen combustion, yielding only about 0.0000001% of the mass converted to energy, a billionth. Nuclear fission, which powers submarines and some proposed space reactors, is far more efficient, with about 0.1% of mass converted, a thousandth. Fusion, the process that powers the sun, converts around 0.7% of mass into energy, close to a hundredth. In stark contrast, antimatter annihilation is nearly 100% efficient, again releasing 1 billion times more energy per kilogram of fuel than chemical rockets, about 140 times more than fusion. This extreme energy density means that an antimatter-powered spaceship would require only a fraction of the fuel that chemical or nuclear propulsion systems need for the same journey. A single gram of antimatter, when annihilated with normal matter, would release as much energy as about 43 kilotons of TNT, roughly equivalent to 3 Hiroshima-scale nuclear explosions. In space travel, this translates to engines that can achieve high thrust while keeping spacecraft mass low, critical for efficient interstellar voyages. Beyond energy density, antimatter propulsion offers an exceptional thrust-to-weight ratio and the potential to reach relativistic speeds. Because antimatter annihilation produces high-energy particles and radiation, it can be harnessed in various ways to generate thrust. Now, the easiest way is just to let a stream of matter and antimatter intersect right behind your ship in some big sturdy rocket nozzle. This requires no advanced technology to operate beyond whatever you use to make and store antimatter. The ideal would probably be a big cold box made of superconducting magnets full of neutral sub-Kelvin particles, for storage anyway. Some other designs propose using the reaction products, such as charged pions, in a magnetic nozzle to produce direct thrust, similar to how ion thrusters work, but with far greater efficiency. Other engine proposals involve using antimatter to trigger microfusion reactions, providing a more controlled release of energy that avoids excessive radiation hazards. I don't want to spend too much time discussing how to produce or store antimatter. We covered that in an episode on antimatter factories a few years back, but I'd rather focus on the propulsion methods. However, before we dive in, let's clear up some common misunderstandings. First, it's important to acknowledge that antimatter annihilation isn't quite as straightforward as it's often portrayed. Some suggest that antimatter could be safely stored by constructing it from exotic particles so that no regular matter of that type exists nearby, with the antimatter only reacting when mixed with a separately stored counterpart at the desired time and place. While this approach has potential if you make it work and is an improvement over the default method of storing charged antimatter particles in magnetic containment devices or neutral charged antimatter in optical traps, it still presents significant challenges. We have had good luck storing chunks of frozen neutral antihydrogen at the sub-Kelvin scale, where it has interesting magnetic properties that let us magnetically levitate it. The idea, however, is that you could have a chunk of antimatter that doesn't immediately explode on contact, perhaps even a solid piece of frozen anti-water. But this approach won't work because it's not just the anti-water molecule or even the individual anti-hydrogen and anti-oxygen atoms that annihilates upon contact with normal matter. In fact, it's not even just the protons and neutrons themselves, which are composed of 3 valence quarks. At the subatomic level, annihilation occurs due to the fundamental particle interactions, not just between valence quarks, but also involving the vast number of C-quarks and gluons that make up the majority of a proton or neutron's mass. The 3 valence quarks, 2 up and 1 down, or 2 down and 1 up quark, for the proton and neutron respectively, account for only about 1% of a nucleon's total mass, while the remaining mass comes from the dynamic interactions of these C-quarks and the strong nuclear force binding them. At this subatomic level, there is a vast amount of nebulous energy fluctuating between non-stable states, lasting for periods that make even nanoseconds seem like an eternity. When an external particle moves through this metastable, seething quantum sea, it can be annihilated, while a new stable or semi-stable particle may emerge. This means that even an exotic particle like an anti-strange quark can be destroyed when interacting with a normal atomic nucleus, not through direct annihilation, but by merging with a quark in the nucleus to form a new particle. For example, an anti-strange quark could combine with an up quark in the nucleus to form a kaon, a type of meson composed of 1 regular up or down quark and 1 strange or anti-strange quark. Kaons are surprisingly long-lived by nuclear standards, surviving for several nanoseconds before undergoing weak decay in particles such as a muon or electron and a neutrino. Notably, this process does not produce photons, highlighting the complexity of particle interactions beyond simple matter-antimatter annihilation. This same principle explains why, in rare cases, when two protons collide with enough force, they can overcome their mutual repulsion and directly interact at the nuclear level. When this happens, one of the protons can transform into a neutron, resulting in the formation of deuterium, a nucleus consisting of one proton and one neutron. The kinetic energy both particles use to overcome the repulsive charge is added to the mass energy to get the extra amount needed for the neutron, which is heavier than a proton and by the same amount a down quark is heavier than an up quark by. Though this event is incredibly rare, it is the fundamental mechanism behind nuclear fusion in stars, and what actually happened there is that you began with 6 quarks, 4 up and 2 down, and ended with 3 up and 3 down, but that up quark didn't mutate into a down quark. Instead it interacted via the weak force, transforming into a down quark while emitting a W+ boson. The W+ boson, in turn, decays almost instantly into a positron and a neutrino. What's often left out in simplified explanations is that this transformation requires an enormous amount of energy, which is only available because of the high-energy collision between the two protons. An up quark has only about half the mass energy of a down quark, making this transition non-trivial. More significantly, the W+ boson has thousands of times the mass energy of either quark, and millions of times the mass energy of the positron and neutrino it decays into. The W+ boson is an extremely short-lived packet of energy, and in many ways this is a useful way to think about all particles. They are simply energy in a structured form. Some are more stable than others, and countless theoretical particles are so unstable that we haven't even found a way to observe them, though they may last for trillions of Planck times, the smallest measurable unit of time in our universe. This still makes their existence fleeting beyond comprehension, as a single Planck time is trillions upon trillions upon trillions of times shorter than a second. And yet time is relative. Stars live a very long time, but the shortest lived ones live less than a millionth as long as longer lived ones. And if we zoomed out to the timelines that black holes lived for, these stars, both short and long-lived, would seem as short-term in comparison to those black holes as the various unstable subatomic particles we just mentioned. Remember, a particle that might live only a millionth of a second might have time to make thousands of orbits around a nucleus. It's only short-term in our scale. Some particles are a lot more stable than others. Protons by themselves and electrons are both thought to be either utterly stable or have half-lives far beyond trillions of years, which still makes them very much mayflies compared to black holes. And massless particles, like the photon and perhaps the graviton if it exists, are also stable and cannot decay when by themselves. Anything can transform when interacting with other matter though. A photon can be absorbed by you or I, for instance. That is how you watch this show, which I hope you are enjoying enough thus far to hit those like and subscribe buttons. Some theories allow for photon decay in a vacuum, such as into a hypothetical axion dark matter particle and a neutrino. Of course, in particle physics, the concept of a vacuum becomes somewhat ambiguous, but the key point is that the photon is an incredibly stable particle. As a result, when subatomic transformations occur, photons frequently emerge, either as primary products or at the end of a chain of interactions and decays. This is especially true in scenarios where particles and their antiparticles exist in roughly equal amounts. When they interact, we often describe the process as annihilation, but in reality, the original particles don't simply vanish, they are replaced by a new set of particles. They are not really annihilated any more than two chemicals interacting to be replaced by some new molecule of a different type. In many cases, the outcome includes a pair of high-energy photons, but it doesn't always have to be a pair or even an even number. The process is dictated by energy conservation and quantum interactions rather than a strict requirement for symmetry in photon production. Needless to say, from a practical perspective, when a large amount of matter is converted into particles like photons that can rapidly escape from nuclei, and when this happens across a massive number of nuclei in a short moment, you get a tremendous explosion. This is the fundamental principle behind a fission-based atomic bomb blast, a more energetic fusion bomb explosion, or the even greater energy release of an antimatter detonation. One simple way to use antimatter efficiently is to inject it into a larger supply of regular matter, such as hydrogen or another propellant. A small amount of antimatter annihilates, releasing immense energy that heats up the surrounding hydrogen, which then expands and is expelled as high-temperature rocket exhaust. This functions similarly to a nuclear thermal rocket, but with far greater energy density. This method is estimated to provide an exhaust velocity of 50 to 100 km per second, which, while nowhere near relativistic speeds, is still significantly higher than chemical rockets, 4.5 km per second, or even nuclear thermal propulsion. This corresponds to a specific impulse of 5,000 to 10,000 seconds, far superior to the 450 seconds of the best chemical fuels. However, while this system isn't practical for interstellar travel, it is highly effective for interplanetary missions, making it an excellent choice for asteroid scouting, comet mining, or rapid maneuvering within the solar system. An antimatter thermal rocket could also be compact and simple, offering far higher thrust-to-weight ratios than ion drives while still being efficient. Additionally, since it only requires antimatter for energy, it can replenish its propellant locally by extracting materials from asteroids, moons, or icy comets, making it a versatile and sustainable option for long-duration space missions. We've talked a lot about anti-proton and anti-hydrogen, and of course an anti-hydrogen atom needs not just an anti-proton nuclei, but also an anti-electron, or a positron. If you're curious, an electron, or its antiparticle the positron, while stable from decay by itself, along with other leptons such as muons and neutrinos, can also transform without necessarily colliding with an antiparticle. So don't assume that a large container of any type of antimatter can simply be stored safely. Nonetheless, it might be easier to contain if it could be stabilized in a cold, solid form or as an exotic material. However, this is precisely why antimatter escaping from storage is dangerous. No matter how it is structured, antimatter will always annihilate upon contact with normal matter at the fundamental level. Although again, in many cases, annihilate is less accurate than react with. But you still don't want to be there when large amounts of it are doing either. For more discussion on antimatter storage, check out our episode dedicated to that topic, antimatter factories. In general, antimatter is contained magnetically or in some cases by keeping neutral antimatter, such as antihydrogen or even conceptual frozen antiwater, from drifting to regular matter using laser confinement. We can also imagine AI dynamically controlling magnetic storage systems, with the penning trap being one of the better known and smaller scale designs. What really matters today, though, is what you can do with antimatter if you can produce and store it safely. The feasibility of making and storing antimatter directly affects the economics of spaceship propulsion and determines whether you are using raw antimatter as fuel or employing tiny amounts for antimatter catalyzed fusion. You might also be wondering how antimatter can catalyze fusion and why this is nice for propulsion, or for that matter, small nukes. This is going to be our slowest and antimatter cheapest approach to use antimatter for propulsion, so it's a good one to start with, especially as it's likely the first one people would use, given the small needs for antimatter compared to other fuel, anywhere from 1,000th the mass or 100,000th being antimatter, and the rest more mundane fusion fuel.
Antimatter catalyzed fusion, ACF, is basically the spark plug approach to fusion propulsion. Instead of trying to power your ship directly with antimatter, which require enormous quantities, you use tiny amounts of it to kick ordinary fusion fuel over the ignition threshold, and this lets you do a potentially tiny fusion drive, ideal for shuttles and missiles, assuming you've got normal fusion working at all. If not, this becomes your method for doing so even for large capital ships. In normal fusion, atomic nuclei have to collide with enough energy to overcome the Coulomb barrier, the natural electric repulsion between positively charged nuclei. That usually means millions of degrees of temperature, like in the Sun or experimental reactors such as tokamaks, which we deep dived earlier this month. But if you inject a small amount of antimatter, typically antiprotons, into a fusion fuel mix like deuterium-tritium or helium-3, those antiprotons annihilate with nearby nucleons and release a burst of energy in the form of pions and gamma rays. That burst acts like a microscopic ignition charge. It locally heats and compresses surrounding fuel, allowing fusion reactions to start much more easily, similar in principle to how fusion bombs ignite thermonuclear weapons, but vastly smaller and more controllable scales. One proposed approach is to inject antiprotons into tiny pellets of fusion fuel, producing a sequence of small micro-explosions that drive fusion reactions in pulses, much like inertial confinement fusion driven by lasers.
The result could be a high-efficiency fusion drive capable of both strong thrust and high exhaust velocity, making one of the more practical ways antimatter might first appear in real spacecraft propulsion. The main challenges of antimatter-catalyzed fusion come from antimatter production, storage, and containment, but it requires far less of these than other versions that involve huge amounts of antimatter. On the other hand, because the overwhelming majority of your energy is coming from fusion, you can only achieve the types of speeds that fusion drives offer, and this technique is basically attempting to achieve a fusion torch drive, if no other method of fusion ends up working out or offering such high speeds as those are hypothesized to do. Think 10 to 20% of light speed as the peak for antimatter catalyzed fusion, as it's basically going to match the ideal fusion drive. As with anything operating under the rocket equation, the maximum speed is about the exhaust velocity of the propellant and the percentage of the ship's total mass given over to it. Ships that don't need to slow down can go twice as fast, or the reverse, if they're being pushed by a beaming system up to speed and just need to slow down. And on an order of 5 to 10% of light speed is what a fusion torch drive would expect its exhaust velocity to be, and about double that is going to be more or less the realistic maximum for an interstellar vessel seeking to speed up and slow down on its own fuel. We'll return to beaming systems and antimatter in a bit. Our next system is the antimatter pion rocket, which can achieve much higher speeds than traditional propulsion methods. A typical proton-antiproton collision primarily releases mesons, which are particles composed of a quark and antiquark. While mesons can technically be any particle containing equal number of quarks and antiquarks, most are just 2, not 4 or 6, and the ones of interest to us here are pions. When a proton-antiproton collision occurs at low to moderate speeds, the primary result is a trio of pions, either 3 neutral pions or a combination of 1 neutral pion and 2 charged pions, 1 positive and 1 negative. At higher collision energies, the interactions can produce kaons, eta mesons, or even charmed quarks, but none of these are final products. Mesons are not long-lived, and pions emerge as the lightest and lowest energy mesons, making them the dominant byproduct of proton-antiproton annihilation at near-rest speeds. Charged pions, pi plus and pi minus, are composed of 1 up quark and 1 down quark, with 1 being an antiparticle. Since up quarks have a mass of roughly 2.2 MeV and down quarks roughly 4.7 MeV, their combined rest mass is minuscule compared to a proton's rest energy of 938 MeV. A proton, composed of 2 up quarks and 1 down quark, only has about 9.1 MeV of its mass in those quarks, meaning over 99% of its mass energy comes from those gluons and C quarks. Similarly, pions have a rest mass between 135 and 140 MeV, about 20 times the combined mass of the 2 quarks that compose them. When 3 pions are produced from a proton-antiproton annihilation, their combined rest mass energy accounts for only about 1/5 of the total initial energy of those annihilated particles. The remaining energy is converted into kinetic energy, which is crucial because it means these pions are moving at relativistic speeds, close to the speed of light, making a good propellant. If these fast-moving pions are directed into a magnetic field, their positive and negative charges cause them to deflect in opposite directions, creating a separation before they decay. This separation occurs over a distance of roughly 1 meter before the pions decay into muons and neutrinos. Muons, the heavier sibling of electrons, travel at similar speeds but have a much longer lifetime, thousands of times longer than a pion, before eventually decaying into an electron or positron and additional neutrinos. Meanwhile, neutral pions decay almost instantly, several billionths of a nanosecond, producing a pair of high-energy gamma photons. This rapid decay and high kinetic energy are what make pions an excellent candidate for propulsion, as their energy can be converted into thrust using a magnetic nozzle, allowing for antimatter-powered spacecraft to achieve near relativistic velocities. The key idea here is that as your hypothetical stream of protons and antiprotons is fired out the back of the ship into a magnetic rocket nozzle, the charged pions produced in their annihilation are pushed backward by the magnetic field, which in turn pushes the ship forward. The exact fate of these pions after they exit the ship isn't particularly important, except for the gamma rays they eventually produce. Any gamma rays emitted in the direction of the ship pose a problem because they can damage ship materials as they are high-energy radiation.
Unlike lower energy photons, which can be reflected with ordinary mirrors, gamma rays have no known reflective material, meaning we can only absorb their momentum rather than redirect it. This is a disadvantage as reflection is far more efficient for propulsion. When you reflect a particle, like using a mirror to reflect a photon or a laser, you effectively double its momentum transfer to the ship, since the reflected particle moves backward with equal and opposite momentum to what it had on arrival. Without reflection, we only get the momentum from emission. If we had a material able to reflect gamma radiation, one of the many cool uses for it would be instantly improving the speed of a ship like this, or one using a Kugelblitz black hole. Another important point is that many of these decays produce neutrinos, which are notoriously difficult to interact with. Neutrinos can pass through a light year of lead without being interrupted, making them entirely useless for thrust purposes. Since they cannot be absorbed or reflected, they contribute nothing to propulsion. Unless, of course, you had some advanced clock tech capable of absorbing or redirecting neutrinos. If such technology existed, neutrinos could actually become an ideal propellant in many ways, given they are near light speed velocities and abundance in high-energy reactions. However, with our current understanding of physics, neutrinos remain a lost energy source, escaping freely into space without contributing to the ship's motion. If you could make them work, maybe have a material able to reflect both gamma rays and neutrinos, then your antimatter rocket might be able to be a pure photon rocket at that point, or nearly so, a straight-up classic matter-to-energy torch drive, and that might be able to allow even 99% of light speed. Our pion rocket is more plausible, with known science and materials though, and it doesn't do too bad on speed itself. The antimatter pion rocket has been under discussion longer than I've been alive, but Sean Westmoreland gave it a deeper look and back in 2010 calculated it could achieve potentially 58% of light speed. And a spaceship is truly relativistic at this point, with a Lorentz gamma factor of 1.23, or an inverse gamma of 0.814, a generally more intuitively useful value. In simple terms, that means those on board the ship think the distance they are traveling has shrunk to 81.4% of normal, while those watching their clocks think they've slowed to 81.4% of normal. The 4.37 light-year distance to Alpha Centauri takes them 7.53 years to make, but when the crew departs, they themselves have only experienced a flight time of 6.13 years. One neat thing about antimatter is that your spaceship doesn't necessarily have to be very large. In fact, it could be smaller than a pencil, with just enough room for a magnetic bottle to store antimatter. Even though natural antimatter sources are rare, and producing even a microgram would still be an impressive feat, the extreme energy density of antimatter means tiny automated ships could still be viable. A small probe carrying a few self-replicating nanobots and a tiny onboard computer might be all that's needed for an interstellar mission. In the most ambitious scenarios, such a probe could serve as a von Neumann self-replicator, capable of reaching a distant star system and constructing an entire colony from local materials, potentially seeding human expansion across the galaxy with minimal initial mass. I should note that antimatter storage bottles and near-atomic scale computers and machinery are far more susceptible to critical damage by radiation than even a human. So lots of frontal shielding is still a good idea and limits how small such devices can be. Realistically, anything short of a meter of dumb material in front of your ship, soaking up radiation, will result in your small and tiny spaceship simply being blown up when some random particle gets inside your antimatter storage container, or bounced around your atomic-scale hard drives. Hence why I often suggest using self-replicating space probes in your own star system to build giant spaceships instead, where you can also keep an eye on them. Or as a vanguard you deploy right in front of your fleet near your arrival, to build some slowdown infrastructure like power collectors and beaming arrays. This is also handy if you want to keep those ships and the antimatter in them away from your own crewed ships, as a few thousand miles of separation makes them quite safe even if they blow up, and then they can go build non-antimatter based slowdown architecture at a new star system. As antimatter is thought to be hard to produce and store, various rationing ways to use it in tandem with other materials have been contemplated, and this includes the antimatter ablated light sail. This technique involves a small supply of anti-hydrogen, maybe just a few grams for smaller ships. This uses anti-hydrogen slowly released toward a forward plate or dish, akin to the Medusa drive, made of uranium-238, which might be as small as a few meters, allowing a relatively small ship. This forward sail is a nice radiation shield too. The antimatter reaction with the U-238 should produce neutrons and other secondary products which would leave the sail at very high speeds, and produce a power rate of a couple megawatts per kilogram of sail. Such ships may be able to gather the necessary antimatter from natural sources such as gas giants. Planets have huge magnetospheres which can act as natural repositories for antimatter to persist for quite some time simply because they are huge and very empty, so the antiparticle can get magnetically trapped there and run around in circles for a long time before bumping into other matter. Lots of things produce antimatter, just almost always in some very dense spot where it is near instantly hit by regular matter again and you get photons. One way to make antimatter and keep it for a while would be to create big supercollider rings around stars powered by them, and big enough to maintain a low density while you extract that antimatter. We often talk about putting large power collectors near stars anyway, often power beam arrays for pushing spaceships to high speed, and this is another approach. You hurl thin beams of antimatter to a spaceship, which it then collects magnetically, gaining all the momentum those particles had and absorbing some of that antimatter for storage, while other bits probably hit in a blade of shield on the back and push it along when they explode. What makes this different from a laser sail or mag sail is that you're not just being pushed by a beam, you're also receiving a resupply of fuel at the same time. This means that if the beam is interrupted, whether due to losing alignment or moving too far for reliable transmission, you're not left drifting aimlessly. Instead, you have a full tank of extremely high energy fuel, allowing you to continue propulsion independently. And your storage might be a thin magnetic ring extended wide out from your ship, on which that sail is spread, and which could have the antimatter in it explode without potentially wrecking your ship's main sections. We have sail designs that are often many miles in radius, or even hundreds of miles in some cases, and even antimatter doesn't explode that powerfully. Sending beams of charged particles is challenging because they naturally repel each other, which can cause them to scatter. However, if the beam can be kept in a single file arrangement, the particles will only push each other forward and backward rather than spreading out sideways, which is manageable. Big receivers at the destination help with this too. Normally this wouldn't be very useful, as even relativistic particles traveling a well-ordered beam wouldn't effectively transport large amounts of material, such as oxygen or hydrogen, for a conventional fuel supply. But in this case, we are not sending a stream of rocket fuel or breathable air, we're sending antimatter. Because antimatter is millions of times more energy dense than conventional fuels, it doesn't need to be sent in high quantities to be useful. Even a sparse, well-contained antimatter beam could provide a spacecraft with a steady, long-range energy supply, vastly improving mission endurance and reducing the need for carrying massive onboard fuel reserves.
One interesting implication of this is economic. If antimatter becomes even moderately practical to produce, it might function not just as fuel, but like a universal energy commodity. I'm normally skeptical of commodity currencies in the future, but for high-level banking between worlds, it meets a lot of criteria we discussed in our interstellar banking episode, particularly being compact, universally valuable, and easy to move at high speeds. Why is that? Well, instead of shipping bulk fuel between planets or star systems, you could ship tiny quantities of antimatter and combine them with ordinary matter at the destination. Because the energy density is so extreme, even small packets represent enormous amounts of usable power. They can also be transmitted at relativistic speed as particle beams or packets. This lets them not only serve as spaceship fuel, but also as mid-voyage refueling methods, which would be particularly critical to resupplying battle fleets between actions. In that sense, antimatter could become a kind of portable energy currency for a spacefaring civilization. A kilogram of antimatter represents roughly 90 quadrillion joules of energy, about the annual electricity consumption of a small city. In an interplanetary or interstellar economy, antimatter might play a role similar to gold bullion, expensive to produce, compact to transport, and valuable anywhere because the physics works the same in every star system. A civilization powered by large solar collectors or stellar-scale industry might export antimatter the way earlier societies exported refined fuels or precious metals. The same infrastructure that manufactures antimatter for starships could also supply energy to distant spacecraft or colonies, turning beams like the one we just described into both propulsion systems and long-range energy supply lines. Today's episode is about one of the most powerful propulsion concepts we've ever considered. But raw power is only part of the story. Any system that handles that much energy has to be built to extreme standards, where precision, reliability, and smart design matter just as much as output. If you enjoy seeing how real-world engineering tackles those challenges, check out Real Engineering, which breaks down design choices behind complex systems, from aircraft to power infrastructure, and why good engineering is often about making things work consistently, not just pushing limits. And that same idea carries over to survival. In my exclusive, Surviving a New Ice Age, we explore how civilization depends on systems that keep working when conditions get harsh and failure is not an option. Nebula is where every episode of SFIA premieres early and ad-free, alongside years of monthly exclusives and content from hundreds of awesome creators. Right now, Nebula is offering 40% off lifetime access, just $300 for permanent access to everything on the platform. Use my link in the QR code to get that deal, and there's also 50% off an annual plan. That's just $30 for the whole year. While these types of beaming systems allow for arbitrarily high speeds, reaching gamma factors of 100 or more, where ships begin to experience significant drag forces from more than just interstellar gas and dust. Even the ambient cosmic microwave background radiation, which is normally harmless, becomes blue shifted to higher energies, creating a real slowing effect. This raises the question of how to decelerate at the destination, especially if there is no beaming system in place to assist with braking. That said, this drag can provide some natural assistance in slowing down. Other major concerns include surviving the journey itself, particularly ensuring that your antimatter storage tanks don't explode due to accident or external interference. Trailing your main storage tanks behind you on long tethers of super strong materials might be wise, and those could be recycled into space elevators in some new system. Outside of colony ships, this might be more worrisome. Even if you arrive intact, will you be welcomed at your destination? And then by greetings and welcomes or by volleys of anti-ship missiles. A ship carrying vast amounts of stored antimatter represents an apocalyptic-level threat, capable of devastation far beyond nuclear weapons. There's also an issue what happens back home. If your civilization has been mass-producing and stockpiling antimatter for decades or centuries, the world you return to may be unrecognizable. Antimatter storage alone is complex enough to warrant its own dedicated discussion. We haven't even touched on advanced containment ideas, such as embedding antihydrogen into fullerenes or graphene structures to improve stability. However, such approaches primarily prevent accidental explosions, not malicious attacks. If antimatter storage is perfected, it introduces new security risks, intentional detonation or sabotage. Consider a simple ballpoint pen, with its ink cartridge replaced by an antimatter containment unit holding just a dozen milligrams of antimatter would release about half a kiloton of explosive energy, just a few percent of the Hiroshima bomb yield, but still equivalent to 500 tons of TNT. That's thousands of car bombs or large artillery shells all packed into a single pen, one much mightier than any sword. And that's assuming only a tiny fraction of the pen's mass is dedicated to antimatter storage. A typical pen is nearly 1,000 times heavier than that fraction I gave. Moreover, antimatter storage is vulnerable to external manipulation, especially via magnetic fields. Density is not your friend when storing antimatter, as magnetic confinement requires space to ensure containment fields remain stable. Worse, most known materials offer only weak magnetic shielding, meaning that even small antimatter containment systems could be triggered remotely using a well-placed electromagnetic pulse (EMP) or external magnetic interference. This makes them particularly susceptible to sabotage or attack if security measures aren't properly accounted for, but also means you can set small ones off at a safe distance, or less dangerous distance anyway. Needless to say, they make for some chilling weapon options, like a pistol that fires nukes with each bullet, and ones often discussed in science fiction, but which may end up as science fact. If you're looking for some suggested reading, Paul Anderson's 1995 novel, Harvest the Fire, explores a fascinating antimatter propulsion design that achieves near-total conversion and collimation of gamma-ray exhaust. This concept has also been explored in depth by Friedwald Winterberg, whose work delves into the technical feasibility of gamma-ray-driven propulsion, though his research is more technical than we'll cover today, especially considering our deep dive into quark interactions earlier. Another notable design is Valkyrie, developed around the same time, which was my own first encounter with an antimatter starship concept. This design theoretically allows a ship to reach 90% of the speed of light or more, making it one of the most ambitious relativistic propulsion concepts ever proposed. Another great example from film is the ISV Venture Star and her series of sister ships from James Cameron's Avatar film franchise.
This is perhaps the best known antimatter ship in popular fiction, and while its science wasn't quite perfect, it was still heads and shoulders more accurate than we usually get in blockbuster films. The Venture Star featured 2 antimatter engines aft of large radiators, which apparently took 2 weeks to completely cool off after the deceleration burn, annihilating antimatter fuel with hydrogen propellant. In that setting, they were able to do this reliably using the unobtainium they all fought over, which most people forget was a room temperature superconductor, something we've done another episode about before, and before they had it, the Venture Star's predecessors required even bigger radiators. Another fun fact about this ship was that when leaving or arriving in Seoul, they used a massive pushing laser and retractable sail, so they could save most of their antimatter fuel for use in Alpha Centauri. Why they didn't build a Stellardrone at Alpha Centauri, or how Earth had any sort of energy crisis while making antimatter and pushing lasers, however, is beyond me. With these 2 systems combined, the Venture Star was able to accelerate or decelerate at 1.5 Gs for 5.5 months, reaching 70% of light speed. As we've seen today, antimatter propulsion presents both incredible opportunities and immense challenges and dangers. It offers theoretical speeds close to the speed of light, an energy density unmatched by anything other than Kugelblitz black holes under known science, and a pathway to interstellar travel that no other fuel source can match. Yet its practical challenges, production, storage, containment, and safety, are enormous.
If we want to reach the stars this way, we need not just safe storage, but production at scale that doesn't wildly cost more energy than it delivers. Today our efficiencies are terrible, though as we discussed in antimatter factories, there are proposals that can prove that by orders of magnitude. However, even if we can't or don't want to achieve bulk production and storage, that does not mean we should dismiss it for all purposes. Even small-scale antimatter usage, like antimatter catalyzed fusion, could revolutionize spaceflight within the next century, providing a stepping stone toward full antimatter propulsion. Let us also remember that the Sun produces about 2 billion times more sunlight than Earth receives. For many centuries to come, we could tap that power with simple, tinfoil-thin collectors in quantities far beyond our own needs, and if antimatter costs 100 times the energy it releases, it might still be an amazingly useful spaceship fuel. If we ever achieve large-scale antimatter production, it could enable interstellar probes, relativistic starships, von Neumann self-replicating machines, and even the classic space opera staples, personal interplanetary spacecraft, and the fast, mobile fleets of the void, so common in science fiction. But even if we can never mass-produce antimatter economically, it's still invaluable for vanguard units like von Neumann probes, machines sent ahead to build infrastructure in new star systems. They could construct power collectors and beaming arrays to help laser-sail ships arrive and unload colonists at fully mapped systems, with some facilities already prepared. You send a small probe with expensive fuel. It builds those collectors at the destination, and it gets followed by your giant generational arc ships, pushed up and down from interstellar speeds by cheaper methods. Whether antimatter becomes the backbone of starflight or remains a specialized tool will mostly come down to economics. If we learn to manufacture it cheap and safely, it might power relativistic ships and fast interstellar commerce. If it remains expensive, it will still have a role, powering the first probes, the vanguard machines that go ahead of us, to build infrastructure in distant systems. Either way, antimatter gives us the closest thing physics offers to a true torch drive. It may not be the engine that carries most of humanity to the stars, but it could very well be the engine that helps us open the road.